We're here looking at AP Physics C, E&M 1999, question 1. This problem's for Sakil Ali, who asked for it on the YouTube. What we're going to be looking at here is a Gauss's Law problem with a conducting sphere, and then we're going to put a spherical capacitor kind of around it, set something up like that. We're going to do some Gauss's Law. We're going to look at some capacitance and looking at potential differences. So it should be a little bit of everything in this problem. If you're looking for this problem, I'll put it at the bottom of the YouTube video, so check the description so you can find that, and you can find the actual solution set in and of itself if you want to look at that specifically, and I'll be walking you through it here. Okay. So starting off, we've got this isolated sphere, and in this isolated sphere, which is right here, it's got a radius of 0.2 meters, and it is at a potential of minus 2,000 volts. Determine the charge Q naught on the sphere. So what we need to do for this is we need to recognize that if we have a charge, we can create a potential out of that. And potential, remember, V is just equal to KQ, and this will be Q naught in our case, over R. Sometimes you'll see this K written as 1 over 4 pi epsilon naught. That is the value for K. It's a slightly easier way to write it for our AP Physics C stuff whenever you're doing some calculus, because the 4's and the pi's will get things to go away. So that's just K Q naught over R. And if we just start plugging in values here, we can just easily say that bringing this 4 pi eps naught over to V and bringing the R over to V, we can say that V times 4 pi eps naught times R equals Q naught. And at that point, it is just a matter of throwing down values. Another way we could do this, if you didn't want to do the 1 over 4 pi, we could just divide by K and then multiply by R. It's a little bit easier to do here. So we can just say V times R over K equals Q naught. When we put in values there, we've got negative 2,000, which is nice because now we know it's going to have a negative charge. The R value is 0.2 meters divided by K, which is 9 times 10 to the 9th. That gives us a Q value here of around 4.4 times 10 to the minus 8. So 4.4 times 10 to the minus 8, and that is in coulombs, C. So a quick little part A, we just had to recognize what was going on with voltages for charges. Okay, so nothing crazy there. And that is because we can determine that a uniform distribution of charges in a spherical shape, all of those charges simply exist. We can kind of think of that as a point charge right there. So that part is pretty much a point charge that's going on. Okay. Part B starts to get a little bit weirder because what we've got now is we're going to put another sphere around our initial solid sphere, so concentrically, and these hemispheres that are going around this have an inner radius of 0.4, so that's the B here, and an outer radius of 0.5. So this is 0.1 meters thick, so 10 centimeters. And they're joined together forming a capacitor, because I've got a conducting region, and then a blank region, and then another conducting region. So just like parallel plates, conductor, blank, conductor. That's what we have here, but just in a sphere shape. And a wire is connected from the outer sphere to the ground and then removed. So it sets everything up in this capacitor kind of way. What we're asked to do to begin with is determine the magnitude of the electric field in the following regions as a function from the distance of the center of the sphere. So as we move from the center of the sphere outward some radial distance r, we'd like to know what these electric fields are. Well, if we are doing this with electric fields, we can actually do this in a really easy and straightforward way. A lot of people would want to go a heavy Gauss's law way here, and that is a fine way of doing it, looking at the closed path integral of the electric field equaling the charge enclosed. But what you can quickly see here, if we look at question B1, where what happens if we're inside this radius A here, Your answer is going to be straight up 0. And the reason it's 0 is because the electric field equals 0 inside a conductor. That's it. Done. You're inside the conductor. It's 0. Likewise, for part 3, where you're inside this conductor here, like that, your E is also 0 because you're in the conductor. Boom, just like that. So that's kind of neat. You just got half of the part B done in half a second. Part 4, and I know we're skipping part 2 for a second, but part 4 down here is also E equals 0. And the reason in this case is there is no net charge. The reason why there's no net charge here is we just said on the inside that this region here with A, it has some negative charge Q naught. When we hooked the outside region up to the ground, we allowed electrons to run away from it. So this outside region now has a charge of positive Q naught. And when we set up our Gaussian spheres on the outside of this, our charge enclosed in this case is positive Q naught minus Q naught, which is 0. And they cancel each other out. So your total charge you've enclosed there is equal to nothing. So your electric field must equal nothing as well. So that's it. So that's how you do number 4. For number 3, or number 2, excuse me, here, it's a little bit harder, but we actually don't even need Gauss's law still. This is amazing. In this, because this is a lovely sphere here, since we've got a sphere in this case, and we're outside of that sphere at some point, at some distance r, we can think of that sphere as just acting as a point charged centered in the center of that sphere. So we know what the electric field is from a point charge. The electric field from a point charge is equal to just kq over r squared. And we already know what q is, this q naught. That's the negative 4.4 times 10 to the 8th coulombs. And we know that r squared is just some value that we're finding this is a function of. So if we go ahead and plug in values here, 9 times 10 to the 9, and then 4.4 times 10 to the minus 8. You could put a negative here. I'm going to admit it because they're just looking for the magnitudes. We don't actually care about the negative over r squared. You get something that's about 400 per r squared Newton coulombs. And once again, we didn't need to do anything for Gauss's law. If you wanted to, you could, but there's no reason to actually here. If you wanted to prove it, and I guess let's just go ahead and prove it. If you wanted to do this with Gauss's law real quick for inside that region, you could say that E dot dA equals the charge enclosed over epsilon naught. And then you'd say, hey, look, I made a sphere. The area of a sphere is 4 pi r squared equals, well, the charge enclosed is q naught over epsilon naught. And all you'd have in this case is that E would equal q naught 1 over 4 pi eps naught. And as we already said, this is just equal to k. And there's an r squared term. So if you want to do this with Gauss's law, you could, way to go, but it acts as a point charge in the end. So if you just recognize that, you could be done with all of part B in about 2 minutes, just saying 0, 0, 0, point charge, all done. So pretty cool thing. If you want to do the Gauss's law, you can do that as well. Okay. So that's kind of cool there. For part C, they're asking us now, Determine the magnitude of the potential difference between the sphere and the conducting shell. So, how do we do this? What's the potential difference between the sphere and the conducting shell? So, let's clear some of this up here. They want us to find what is the voltage here and what is the voltage here and what's the difference between them. So we can do this in a few different ways. One way we can do this, and arguably the easier way if you recognize it, is to just recognize, and I'm going to call this here, that's VA, and then out here is going to be VB. Okay. If all we're looking for is the potential difference here, then that delta V is just whatever the voltage at B is minus the voltage at A. That's all that is. And if you wanted to get that, we could just recognize that by just taking the voltage at those positions and subtracting them, we're fine. And knowing that voltage is just equal to KQ over R, that would just give us here an answer of KQ naught over B minus KQ naught over A. And that would be it. If we plugged in the values for B, which were 0.4, and the values for A, 0.2, and we just plugged in values of K's and Q's, whatever they are, we end up getting something of around 1,000 volts. But that's the really quick, easy way to do that. Just recognize that you essentially have point charges here, and you just do it that way. If you're like, oh, but calculus, that's my jam, I want to do it. Okay, that's fine. In that case, we can recognize that the change in voltage is equal to the negative of the integral from A to B of the electric field through the radial vector you put it. And in this case, this is going to give us KQ, well, negative. We don't care about the negative in the end. We're looking for a magnitude, right? So ignore that. But there is a normally negative there. But we've got KQ by the integral from A to B of this value dr over r squared. Whenever we integrate this, there'd be a negative that kicks out. Once again, we don't care about it because it's a magnitude problem. And we're going to just get KQ times the quantity, well, Q naught, 1 over R from the bounds of A to B, which means that this will just be KQ times 1 over B minus 1 over A, which is literally the same thing we have up here. So if you wanted to do it the calculus method, you're more than happy to, but nothing changes. Okay? So that's just kind of a neat thing regarding that. So once again, point charges are just as easy as doing the calculus. If you're struggling with the calc, maybe it's your first year in calculus, maybe you're not exactly sure what's going on there, recognize, because we've got nice spherical shapes here, we can just start thinking of things enclosed inside of them as point charges and get away with the point charge problem here. Okay. There's another way to do this, but you actually have to do part D before part C. So we're going to pretend we're going just through the problem and we won't have something, but you can see the alternate solution if you've got the solution menu out there. But for part D here, we do have a spherical capacitor here, so what's the capacitance that we've got? In this case, we know for capacitors, the capacitance is just equal to Q naught over a voltage, and now we know everything we've got here. Remember, this voltage, it's between the plates. Okay? Normally for a parallel plate, that's easier to identify. For our plates here, that's going from the inner region A to the inner region B. So this voltage we have here, this voltage is the 1,000 volts that we just found right up here. Okay? Some people want to put the negative 2,000 before in the problem, but that's not true. We're looking for the potential difference between the plates, and that's the value we just found in part C. But with this now, we can just say that the capacitance is equal to Q naught, which was the 4.4 times 10 to the minus 8 coulombs. Once again, I've omitted a negative because they're asking for, we really don't care about positive or negatives in this case. We just want the total capacitance. And when we divide that, we're dividing it by the 1,000 volts we found previously. And when we do this, we get something 4.4, because that's like 4.4 divided by 1. And since we got 1, 2, 3 zeros in the denominator, when we bring that to the numerator, that's going to make that negative 8 smaller. So it's going to be times 10 to the negative 8, 9, 10, 11, negative 11th. And those are in farads. Okay? So that's a quick way we can do that right there. There's another way. If you know the equation for a spherical capacitor, you could use that. I don't think at the high school level a lot of people teach that, but here it is. We're not going to go through a full-blown way of how to get it, but if you happen to know that the equation of a spherical capacitor is 4 pi epsilon naught radius A, radius B divided by radius of B minus radius of A, then way to go. You just did it. You could just straight up use that and you'll get the same exact answer. But this is for a capacitance of a spherical capacitor. But not a lot of people know that. I wouldn't really worry about it. Just recognize what you've done previously, which is this equation, and that this is the voltage, the potential difference between the plates. Okay? So with that, that was a Gauss's problem that wasn't really a Gauss's problem because we kind of got out of it, and we just kind of churned through a lot of point charges things there. So with that, this problem's finished. Adios.